this problem last week? Did we study this problem last week? Do you remember? Do you try this problem before? Did you try this problem before? Last week? Hello? All right. But I mentioned how to solve the problem, right? I mean, the general method. Yeah, I mentioned that. Let me check. This is what we learn, right? So I show you the formula here, and then I mentioned this example, but I haven't solved the problem. Correct? That's right. So I already mentioned this, right? I already mentioned the formula to get the confidence interval for the mean value, but I haven't mentioned this one. Am I right?
Yes, sir.
Okay. All right. All right. Let's try this problem. Let's try the problem. Do you know? By the way, do you know how to solve the problem? Do you know how to solve it? Well, actually, you need to. This is the formula you need to use. Suppose that M is the population mean. Okay. Suppose that M is the mean bit stop time. Okay, this is M, and then you want to construct a 99% confidence interval. So M is X bar plus or minus the Z value times sigma over the square root of N. Is that okay? All right. So you want to get a confidence interval. Am I right? Okay. This is the way you do it. The average value, the sample mean, is simply 12.9 seconds plus or minus the value Z. Sigma is 0.19, so you get 0.19 over the square root of N, and in this case is 32. All right, and then you need to determine this value. How can you determine that value, the Z value? You get the confidence level, that is 99%, so you get 99% here. The area of the two tails should be alpha equals 1 minus gamma, and you get 0.01. And because you have two tails, the distribution is symmetric. Then you get 0.005 here, and we are using the standard of distribution. So this point is simply 2.58. Okay, and you get 2.58 here. Is that all clear, everybody? Please ask me if you have a question. Is this all right?
Teachers?
Yes.
I want to ask that if we do in the exam, so how many decimal number should we take for the Z alpha?
It should be mentioned in the exam. You should read the introduction very easily, instructions very easily, and you can get it. You can get it there. But the very useful the useful value should be 4 decimal places. So you need to route the values up to 4 decimal places.
Yeah, okay. Thank you, sir.
Yeah, but it should be mentioned with all details in the exam. So you should read the instructions carefully. That's all. All right. Okay. All right. That is the That is the first example. Now I want to mention the one-sided confidence interval. All right, how can we do it? How can we get a one-sided confidence interval for the population mean? How can we construct an upper one-sided 95% confidence interval for the population mean? What do you think? Explain again the number 2.58. Well, for the value 2.58, sometimes please just turn on your microphone, because maybe I may miss your comments. For this value, you can see that over here, you get the area to the right is 0.05, right? So I come up with this. And it gets this is 0.005 and this is 0.995. Okay, and you need to determine this point. And where is that point? The area to the left is 0.995, and you may want to have a look at the table. You may have a look at the table. Where is that? Just give me a minute. I'm going to make a copy of the table, and you need to use the normal distribution table for that. All right, so you have a look at this table. You will see that you need to look for, because the areas you want to use the areas to the left. That's why I will use the number 0.995 instead of 0.05. And then you come up with the value 0.995. What is that? Right here. This is the closest number, right? And it gets 2.58. Is it okay? Is this all right? You guys? Is that good? Okay. Let's go back to this problem. Do you know how to construct an upper one-sided 95% confidence interval for the population mean? Do you know how to do that? This is the one that you should use. This is the one we want to use. Okay. So this is the formula for an upper confidence bound, or a so-called right-sided confidence interval. And this is for the left-sided confidence interval. Now you want to get an upper one-sided 95% confidence interval. It means that you want to get the right-sided confidence interval, right? You want to use this formula. Can you tell me? Think about that for a minute and tell me your answer. when you have a one-sided confidence interval, then you have only one bound, one finite bound. The other end should be infinity. A right-sided confidence interval, right? Then you come up with this. You get mu is less than or equals to the upper bound x bar plus, all right, not minus, just plus c alpha times sigma over the square root of n. Okay. And this becomes, what is x bar? You get 12.9 for the sample mean, the z value, all right? And sigma is simply 0.19, correct? Over the square root of n, and in this case is 32, okay? And in order to determine this point, that is the alpha, and you get this area alpha, gamma is 95%. So this becomes 0.05, all right? And this is simply 1.64, right? 1.64. Understand? Is that a question so far? Is there any questions? So you get 12.9 plus, let's say, I'm going to use 1.64 for that, times, what is that? Times the value is 0.19 over the square root of n, and in this case is 32. And you get 18.40836. All right. And then you have the a confidence interval, which is minus infinity to 18.40836. Understand? This is your right-sided confidence interval. Okay. Is there any question so far? Is that all clear?
Sir, the number 1.64 you also took from the table, right?
Yeah, that's right. I used that number from the table. If I use the from the software to get the more accurate value, and this is the one I get. Okay, so this is the one I get if I use the software. All right, makes sense? Is that all clear?
Yes, sir.
Sir, I think that's the standard deviation is 0.19.
Oh yeah, you 0.19. You are correct. Let me check.
Yes.
Perhaps because of typo. Let me see. 0. 0.19, right? I agree. I totally agree. This is the one I get. All right. Let me check it again. 0.19, right? 0.19, 12.9. Okay. Is that a question so far? Is that all clear? All right. Okay. All right. Now I want to move to the next case. In the first case, we consider the set of observations where they follow the same normal distribution and they are independent. Okay. And then sigma square is known. All right. And then you get and then you have all these formulas. All right. You have all the formulas here. Oh, by the way, in this formula you have sigma over the square root of n. There's a name for this. I want to mention that. This is called the standard error. Okay, so the standard error is simply the standard deviation of the approximation of x bar. So right, so the standard deviation of x bar. That is the standard error. Okay. Okay, so the standard error is simply the standard deviation over the square root of n. Let's go back to this. So you need to know sigma square to be able to get to use this formula, right? You have sigma over the square root of n, you get the standard error, and then you can get the error, and then you get a confidence interval. If you don't know sigma, how can you get a confidence interval for the mean value? That is the second case that we are going to study. X1, Xn, they are independent. They follow a normal distribution with the same mean, the same variance. Okay. However, sigma square is unknown. All right. Is that all right? Okay. Okay, so you get well, again, gamma, the confidence level, is the probability that you are correct h bar minus m is less than epsilon, right? And because you don't know sigma, it is very natural to approximate sigma by s. So you get the probability x bar minus m over s over the square root of n, the absolute value less than epsilon over s over the square root of n. Okay. All right, and then I will, on the other hand, we knew that x bar minus m over s over the square root of n. Let's say this is t. It follows a t distribution n minus 1. All right, and I will tell you about this distribution later. So after all, you get the absolute value of t less than the right hand side c, where c is this one. Okay. All right. So now we want to talk about the distribution, the t distribution. What is that? This is the graph of the student distribution. All right. and the standard normal distribution. The black curve is the density curve, the density function of the standard normal distribution. The red curve is the student distribution with degree of freedom 15. There is one parameter in the student distribution. You can call it student distribution, or you can call it a t distribution. And it has one parameter which is called degree of freedom. Okay. There is one parameter, and if the degree of freedom is 15, you see that the student distribution is close to the standard normal distribution. If the degree of freedom is only 2 or less small, then the student distribution is not the same. It's not close to the standard normal distribution. Okay, so you can check to see that the greater the degree of freedom, the closer the student distribution to the standard normal distribution. All right, is that all clear? Okay. The student distribution looks very similar to the standard normal distribution. All right. The only difference, the thing difference between them is that you can have a look at the tail, and the student distribution have heavier tails than the standard normal distribution does, right? So just like you have more times to observe the values far from the center. That's all. Okay. Okay. Now let's go back to our problem. Because we do know that the distribution of t, then I can draw the graph here. This is the student distribution, and you get a confidence level, which is gamma. You have two tails, alpha over 2 here, and alpha over 2 over there. Okay, and you are using the t distribution with degree of freedom. That degree of freedom is n-1, where n is the number of observations. And then you can determine this point. This point is denoted by t alpha over 2, which is the value such that the area to the right is alpha over 2. Okay. All right. You can use the table or the software to determine the point. All right. And as long as you get the value of c, which is t alpha over 2, you can solve for epsilon over s over the square root of n. Then epsilon becomes t alpha over 2 times s over the square root of n. This factor is called the estimated. You call it the estimated standard error. Do you understand? Is that clear? May I move on? Is that all right? This is just your free information, which summarized what I just mentioned. If the xi are independent and they follow the same number distribution with the mean, the same variance sigma square, then mu equals mu hat plus or minus t alpha over 2 times s over the square root of n, where mu is the population mean, mu hat is the sample mean, t alpha over 2 is the value that you can obtain from the table, s is the standard deviation, the sample standard deviation, and n is the sample size. Okay? That makes sense to you, everybody? Okay, if you understand that, let's try this sample. 11 randomly selected automobiles were stopped and the tread depth of the right front tire was measured. The sample mean was 0.32 inch and the sample standard deviation was 0.08 inch. Find the 95% confidence interval of the mean depth. Assume that the variable is approximately normally distributed. Can you do that? Is that some of you got the answer? Let's give it a try. There are several numbers you can see here. 11 is n, 0.08, 0.32, 95%. All right, that's it. N is the sample size. 0.32 is the sample mean. 0.08 is not sigma. It is S. Okay, it is the sample standard deviation. All right. Just to be careful with the word here, sample standard deviation. Okay. Suppose that m is the mean depth. That is m. Then you have the assumption that it is normally distributed. So m equals x bar plus or minus. If I mention nothing, then and I just ask you to get a confidence interval. It means that you want to get a two-sided confidence interval, right? X bar plus or minus the t value times the estimated standard error, which is s over the square root of n. X bar is 0.32 plus or minus the t value. S is 0.08 and n is simply 11. Okay. And how can you get the t value? How can you get the t value? In order to get the t value, you need to have a look at the gamma, which is 95%. And you get alpha equals, well, actually, alpha is 0.05, and this is alpha over 2, so you get 0.025. Okay. And this is the t value. And what is that? You can the degree of freedom. Yeah, using the t distribution with degree of freedom. 11 minus 10 minus 1, so you get 10. All right. And now we are using the table. You need to use the student distribution table to get the answer. All right. And this is what you get. You can have a look at the look for the degree of freedom, which is the column, and that is 10. And then the areas to the right, it is the area to the right, not to the left. The areas to the right is 0.025, right? So you get 0.025. This is the one. Then you come up with the number 2.228. Okay, so I get 2.228 here, and it should be 2.228. Is that clear, everyone? That's all clear?
Yes, sir.
Yes.
All right, thank you. Okay, let's move on to the next question.
Teacher, can you zoom out the table so that I can screenshot it?
You can find the table from the BK Learning. I already uploaded the file.
Okay, thank you, sir.
Yeah, that's much better. Yeah. Let's try this example. 5 independent measurements of the point of inflammation of the diesel oil gave the values in degree Fahrenheit, 144, 147, 147, 146, 144, 142. Assuming normality, determine a 99% confidence interval for the mean. All right, can you do that? Please think about that for a minute and tell me your answer. You come up with the numbers. Let's say 144, 147, 146, 144, 142. All right. And then you need to determine the sample mean H bar, which is 144 plus 142, all divided by 5, and you get 144.6. That is the sample mean. The sample variance, what is that? Well, you get 144 minus 144.6 square plus 142 minus 144.6 square divided by 5 minus 1. And what is that? You get 3.8. Okay, you get 3.8. So in order to get a confidence interval, it is m equals x bar plus or minus the z value, t value, in fact, times the square root of n squared over n. And x bar is 144.6 plus or minus the t value times the square root of 3.8 divided by n, which is 5. And then you get the value here. What is that number? In order to get that number, you need to draw the graph here, and the confidence level is 99%. And this is alpha over 2, and you get 0.005. They are using the t-distribution with degree of freedom of 4, right? Because there are 5 observations. And then you can have a look at the table here, and you look for, let me see, you get 4 for the degree of freedom, and the areas to the right is 0.005. This is the one. So you come up with the number 4.604. It is 4.604 So I have what 4.604. All right, and the calculations will show you the final answer. So this is what you can get for the confidence interval. You get 4.014. So I get 144.6 plus or minus is that 4.014. Okay, so you can do the calculations to get a confidence interval for the mean value. All right, is that a question so far, everybody? Is this all right? Is this all right?
Yes, sir.
Okay. Okay. All right. So for the first two cases, you can see that you need the assumptions that they are independent and they follow the same normal distribution. What if you don't know the distribution? What if you don't know the distribution? So the third case should be x1, xn. They are independent and they follow the same distribution, but that distribution may not be normal. Okay. So the mean is still m, the variance is sigma square, but you don't know if it follows the normal distribution or not. Okay. Then how can you solve the problem? You can go back to here to see that this is the main idea of your arguments, right? You need to use this one. This is the key point. As long as you know the distribution, you can get a confidence interval, right? Because that will help you to deal with the probability. That's all you have to do. And you need to know this one, all right? However, back to this. How can I get a confidence interval for, how can I get the distribution of x bar if I don't even know the distribution of xi? Well, x bar is x1 plus up to xn divided by n. And you don't know the distribution of x1, you don't know the distribution of x2, you don't know the distribution of all these things. How can we get the distribution of x bar? No way. There's no way that you can get it. But we are very lucky because if n is large enough, the central limit theorem helps you to approximate the distribution of x bar. So x bar minus m over sigma over the square root of n approximately follows the standard normal distribution when n is large enough. Okay, when n is large enough. Is that clear? All right. You can also approximate sigma by s if you don't know sigma. So you get x bar minus m over s over the square root of n. That approximately follow the standard normal distribution either. All right, so you can say this is z, this is also z. So if you know sigma, you should use the first one. If you don't know sigma, you can use the second one to approximate it. Okay? Is there any questions so far, everybody? That should be okay, right? All right, may I move on?
Yes, sir.
Okay, great. Yeah, because I'm still waiting for you guys. Hello, can you hear me? Is this all right?
Yes.
Okay, good. All right. So based on this, you can get a confidence interval for the mean value, but it is not the exact. It is not the exact. It is not an exact confidence interval. It is an approximate confidence interval. It is an approximate confidence interval. All right. So I would say that m close to x bar plus or minus the value times sigma over the square root of n. There are two things that you should notice. It should be sigma here, and it should be an approximation, right? And if you don't know sigma, and you use z, all right? You use z. Now, if you don't know sigma, then you can approximate sigma by s to get x bar plus or minus z alpha over 2 times s over the square root of n. Okay? Is that the question so far, everybody? Is this all right? Good. Let's try. Perhaps let's have a break. Then after that, we can try the following example. Okay, let's have a break. Suppose that m is the true average equal duration. That's m. So you get and this is the sample mean, right? H bar, and the sample standard deviation 0.34. That is s. Then I can get m equals x bar approximate plus or minus the alpha over 2 times s over the square root of n. And then you get what is x bar? 0.81 plus or minus the alpha over 2 times s, which is 0.34 over the square root of n, and in this case is 110. So what is that number? In order to get that number, you get the confidence level is 99%, and this is 0.005. Okay, you get that one and this one. You are using the standard normal distribution. All right, you get n01. What is this point? Can you tell me? What is this point? The point here is the z value, right? And what is that number? What is that number? The number here is 2.58. We did use the similar arguments that we did before. And you get 2.58 here, and you can get a confidence interval for the mean value. All right? Okay. If that's all right, everybody? Is this okay? Okay. May I move on? Okay, so this is the one we did. Now I want to talk about a special case, a particular application of the third case, and then I will say the fourth case. But it is not really the fourth case. Maybe it's better to say 3 prime. Okay. Suppose that you get all the x1, xn follow the same Bernoulli distribution with the parameter p, and again they are still they are independent and having the same distribution. Okay, so I get Then we assume here it means that you get all the xi takes the value 1 or 0 with probability p or q respectively, and then I can find the mean of xi, the mean of x, all right, which is p, and you can approximate this one by p hat, okay. This p is called the population, the population proportion. And this p hat is called the sample proportion. All right. Okay. The mean of xi is simply the value m, right? That is the mean, and p hat is simply the x bar, the approximation of the population proportion, and you get the x bar, and that is the sample mean. So m is the population mean, x bar is the sample mean, and they are corresponding to p and p hat. Okay, you can also find the variance of xi, which is p times q. All right, and again you can approximate p by p hat, and you can also approximate q by q hat. Okay, and obviously this one is the variance is sigma square, and the p hat q hat is simply the s square that we talk about in the previous cases. So now go back to the confidence interval. You get m equals to x bar plus or minus c alpha over 2 times the square root of s squared over n, right? N becomes p, x bar becomes p hat. You still get c alpha over 2. You get the square root of s squared is p hat and q hat, and then over n. Is it okay? And this is the formula that you can use to get a confidence interval for the proportion. All right. Okay. This is what. So let's say this is the summary of what I just mentioned. All right. You can also get a one-sided confidence interval for the mean for the proportion. Okay. Let's consider the following example. What do you get? Well, in this case, suppose that P is the long-run proportion of all such trials that was resulted in ignition, and you want to get a confidence interval for the proportion. Then you get P is P hat plus or minus the Z value, right, times the estimated standard error, which is P hat Q hat over n. P hat in this case is 16 over 45. Then you get 16 over 45 plus or minus the z value times the square root of 16 over 45 times 1 minus 16 over 45 divided by n, which is 45. How about the z value? In order to get the z value, you need to have a look at the confidence level, which is 95%. So this is 95%. You get that one. How about this point? This is gonna be, well, alpha is simply 0.05, so you get 0.025 for the right tail. And you can use and you are using the standard number distribution, you can use the table to get that number, right? It is 1.96 here, approximately 1.96, you get 1.96. And then you can use the calculations to get the final answer. All right. Is there any questions so far, everybody? Is that all clear? May I move on? May I move on? Okay. All right. This is the outline of what we just learned in this chapter. You can have a look at this. There are three main cases, right? The distribution could be normal and you know the variance. The distribution is normal and you don't know the population variance. The distributions is not normal, okay, or maybe unknown. And then you have the assumptions that the actual assumption that n is big enough. Okay, that makes sense. So you can you get this. You have this one, and you can use the standard normal distribution or the student distribution to get the answer. All right. And the only case in which you use the t-distribution is when the distribution is of the observations is normal and you don't know the population variance. Okay. In other cases, you need to use the standard normal distribution to get the exact confidence interval or an approximate confidence interval. All right. Any questions so far?
Teachers, I want to ask a question.
Mm-hmm.
What is the value of n that ensure that it is big enough so that we can use the formula at the end? Yeah, the last formula.
Oh, the last one. Well, that is a very good question. In fact, in the exam, then you need to use the number 30. So if n is greater than 30, you can consider n as a big number, and then you can use this approach to construct a confidence interval. However, in reality, this is not the case. Okay, we don't have that magic number. All right. Suppose that you have, if you draw the histogram and you get something like this, then, well, 30, 40 could be enough for you. But if you have a heavily skewed distribution, something like that, then I don't think 30 is big enough for you. Okay, you need at least 100 observations, I think. And if you have something even heavy, even more skewed like that, then perhaps 1,000 is required. Okay, so we don't really have a fixed number to conclude whether it is big enough or not. But for the exam, 30 is fine. Okay.
Yes, thank you, sir.
Yeah. Is there any other questions? Any other questions, you guys? Okay, if you don't, I want to ask you this question. And if you understand it, then you actually understand. If you can answer the question, yeah, then you actually understand the whole chapter. Okay, now please have a look at this. Look at the table. There are two rows, right? One row is related to one data set. So you have two variables here. You have x and y. Can you construct a confidence interval for x and a confidence interval for y? Can you do that? Think about that for 5 minutes and tell me the method that you can use to answer the question. Which method, you guys? We have many methods here. Which one should I use?
I think that's the second one.
The second? Why is that?
Yeah, because we don't have the. Oh yeah, wait. I think that because we don't have the variant yet.
Mm-hmm.
Yeah, and the numbers, the sample size is only 10, so it's quite small.
Okay.
Yeah.
So you use this one, right?
Yeah.
Use the second. Okay. That is good start. So in order to do this, you use this one. If you know sigma square, can I use this one? If I know sigma square, let's say, for example, for the first case, suppose that sigma square is 1. I know that. Should I use the second approach? Can I use the second approach?
I think we should use the first one.
But can I use the second?
I don't know.
Well, some say yes, some say no. In fact, you can use it. All right, you can use it, even though it is not a good idea. Okay. If you know sigma square and the distribution is normal, you should use the first approach, because that gives you a better approximation. Understand? It gives you the better value. If you don't know sigma square, then you can use the second approach. But if you know the value of sigma, then you should use the first one. Okay, is that clear, everybody? Is this all right? It is all right. Okay, all right. Now, so you say that we can use the second approach for both x and y, correct? So it seems that x and y are quite similar to each other, right? And we can use the same method. Am I right? However, that is not true. That is not true, and that is the point. If you have a look at the two data sets, they look very similar to each other. So, suppose that your friend got the first set, and you get the second one, and your friend used one method, and you try to follow his or her protocol, and then you expect to get a correct answer. However, it is not. That is the problem. Okay? Can you tell me the problem here? Can you tell me the problem here? Anyone?
Can you repeat the question one again, sir?
Well, it seems that the two data sets, x and y, are different. I'm sorry, are similar to each other, right? For x, you have 10 observations. For y, you have 10 observations. And they are just numbered from 0 to 10. All right, so it seems that you can use the same method to construct confidence intervals for x and y. Am I right? Is that right? However, that is not true. That is not true. Can you tell me the problem here? Is there any trouble?
Sir, I think that the standard deviation of the y random variable is really is much more larger than for x.
Well, if it's big, it doesn't matter, right? If it's big, you just use s. You just use s. If it is 10, you use 10. If it is 3, you use 3. So if the standard deviation is big, it means that the error you get is big. That's all. But it doesn't mean that. But my question is about something different. Can we use the same formula or the same method to construct a confidence interval for action y? Well, if you have a look at them, the answer seems yes, right? It seems that they are similar to each other. However, you have to be careful with your analysis. You need to have a look at the condition. You need to check first. What is that? Normal. Do not look at no sigma square and no sigma square. The first thing you need to check is normal. Is that a normal distribution? You need to check for the normality, right? Is that a normal distribution? Okay, now I'm going to draw the graph, the histogram of the two data sets. And this is what I get. Okay, for the first one, you can get something like this, right? And it seems that we may have a normal distribution. I'm not sure if this is normal or not, but it could be a normal distribution, right? By looking at the graph here, we don't see any really strange to conclude that it is not a normal distribution. Okay, and in fact, I did use a normal distribution to generate this data set. For the second one, you have a look at this and you see this is the curve we can get, and obviously it is not a normal distribution, and in fact it looks very similar to an exponential distribution. All right, so this is not normal. It is heavily skewed, and because it is not normal, it is not symmetric, it is skewed. Therefore, we cannot use this approach, the second approach. Okay, for the first one, we can use this one. For the second, you cannot. Is that clear? If that's all clear. Okay, yes, so you have to be careful. And that is what you have to do. The software can help you with the calculations, but the software cannot help you to determine which method that you should use for now. Okay, you have to make that decision. Okay, all right. So that is the end of this chapter. Do you have any other questions before we move to the next chapter? Move on to the next chapter. In the next chapter, I'm going to talk about hypothesis testing. In this chapter, I already mentioned how to construct a confidence interval. So you have experiments, you get the observations, you can get the approximation of the mean value, and you want to get the error for that approximation. Okay. And the interval you obtained is called a confidence interval. Now I don't want to only talk about the approximation. I want to test a hypothesis. Okay. What is a hypothesis? what is a hypothesis? And what does it mean by testing? So I want to you to understand these two words, hypothesis. A hypothesis or statistical hypothesis is a claim or assertion or a statement either about the value of a single parameter, the values of several parameters, or about the form of entire probability distribution. For example, you may say the hypothesis is that the velocity is 50 centimeters per second, or the velocity is not equal to 50 centimeters per second. Okay. There are two kinds of hypotheses we have to deal with in this chapter: the null hypothesis and alternative hypothesis. The null hypothesis, denoted by H0, is the claim that is initially assumed to be true. All right, I will talk about that later. But there are two kinds of hypothesis, and the null hypothesis is the claim that you assume to be true at the beginning. And the alternative hypothesis, denoted by H1, is the claim which is the opposite statement of H0. So it contradicts with the null hypothesis. Okay, that's why when you have a look at the H0 and H1 here, you can see that for the H0, the mean value is 50 centimeters per second, and H1 is that the velocity is not equal to 50 centimeters per second. Okay, is there any question so far? All right, and the test of hypothesis is a method in which you use some data set to make the decision whether the null hypothesis should be rejected. Okay. Now, over here, we have several kinds of alternative hypothesis. We get a one-sided alternative hypothesis, in which the velocity is greater than 50 centimeters per second. Okay, or it could be the velocity is less than 50 centimeters per second. Okay, so if H1 is that the mean is greater than 50, then H0 is that the mean is less than or equals to 50. If H1 is that the mean is less than 50, then H0 is that the mean is greater than or equal to 50. Okay. For the two-sided alternative hypothesis, you get H1 is that the mean value is not equal to 50, and then the known hypothesis is the opposite statement, which is the mean is 50. Okay, so there are three scenarios here that you need to deal with in this chapter. All right. Any questions so far, everybody? That should be okay, right? Okay, now I want to Now I want to check to talk about this one. What is a test of hypothesis? A test of hypothesis is a procedure that leads to a decision about a particular hypothesis. And there are two possible conclusions. You can reject the null hypothesis or you fail to reject the null hypothesis. Okay? At the beginning, we assume that the null hypothesis is true, and then you do something. This is an algorithm. Okay? And with this algorithm, you can compute a statistic, which is a value. Be careful, you call it statistic. Not statistic, not statistics. Okay, this is statistic. It is a value, a number, and statistics is a measure. Okay, it is a number, and this one is a measure. Okay, they are different. So by using this algorithm, you can get a statistic, a value, and the rejection region, which is an interval. Okay, a set of numbers. Okay, and if the statistic you compute does not belong to the rejection region, we fail to reject the null hypothesis. That is your conclusion. If the statistic you obtained belongs to the rejection region, then we can reject the null hypothesis, which means that we support the alternative hypothesis, or let's say we strongly believe that the alternative hypothesis is true. Do you understand? Is there any question so far? May I move on? That is what you do in exam. In reality, the procedure is a little bit different. Quite the same, but different. You see that the first case for the first step is just the same thing. You still assume that the null hypothesis is true, and you also compute a statistic. However, we don't compute, you don't determine the rejection region. Instead, you determine the p-value. And based on this p-value, you can make a decision. If the p-value is greater than or equal to alpha, then you will reject the null hypothesis. If it is less than alpha, then we then we can reject the null hypothesis, and then we can support the alternative hypothesis. Is that all clear, everybody? May I move on? May I move on? Okay.
Yes, sir.
Is that all clear? Okay, good. All right. So now, if you have a look at this, you can see that the in this diagram you can support H1, but there is no way that you can support H0. Am I right? Because when you say we fail to reject the null hypothesis, it does not mean that the null hypothesis is true. Understand? So if you say that you reject the null hypothesis, then we think that we have enough evidence to believe that S0 is false. Okay? But for this, you cannot say anything. Okay? No further conclusion. You cannot say that we cannot strongly believe that S0 is false. We cannot strongly believe that S0 is true. It just say that we don't have enough evidence to say that it is false. but we don't know if it is false or true. Do you understand? Is that clear? Is that all right? Okay. May I move on?
Yes, sir.
All right. Now I want to talk about the errors. Oh, by the way, this is the way you do in reality. Okay, but in the exam, you don't have enough you don't have the software with you to compute the p-value. That's why you need to determine the rejection region. Okay. Now you get that's a, if the you can make some error with your conclusion. The null hypothesis is when the hypothesis is true, and you fail to reject the null hypothesis, it means that you don't reject it. Then you make no error. If the null hypothesis is false, and you can't reject the hypothesis, then you make no error either. All right, so that is really good. However, the test is not perfect, right? And you can make some error. The type 1 error is the error you make when you reject the hypothesis even though it is true. If the hypothesis is false and you cannot reject the null hypothesis, you make another error, and that is called a time 2 error. Do you understand? Is it okay? All right. You want to control these 2 errors, and you want to reduce the times that you can make those errors, right? That's why we want to consider the probability of making the errors. The probability of a type 1 error is called the significance level of the test, and is usually denoted by alpha, where alpha is the probability of type 1 error. All right. So alpha is the probability that you make an error, right? Make a type 1 error. So you reject the hypothesis when it is true. Because a type 1 error is usually more serious than a type 2 error, then in this course, we mainly focus on the value of alpha, okay? The significance level. Understand? So, type 1 error is like you put an innocent person to jail, right? And type 2 error is like you cannot put a guilty person to jail. Then in general, the type 1 error is more serious. How about beta? Beta is the probability of making a type 2 error. That is the probability that you cannot reject the null hypothesis when it is false. If you have a look at 1 minus beta, you can get the probability that you can reject the null hypothesis when it is false. All right? And actually, you really want that, okay? So 1 minus beta give you the probability that you can reject the null hypothesis when it is false, and that is called the power of test. Okay, the power of the test. If the power of the test is big, then you have great chance to reject the null hypothesis when it is false. Okay, if the power of the test is small, then you don't have really much chance to reject the null hypothesis when it is false. So obviously, the greater the power, the better. Am I right? Okay. Now I want to ask you a question. let's have a look at this one. Suppose that this is the math. Do you think that probability is a part of math? Do you think that probability is a part of math? Hello? Do you think so?
Yes, sir.
Yes, okay. All right, now, how about statistics? Do you think that statistics is a part of math or a part of probability? Do you think so? Probably. Why? Why is that? Why do you think that statistics is a part of math? So it's just like you have to deal with numbers. That's why you think it is. You have to deal with number formulas. That's why you need to deal with statistics. You need to do. You think that it is a part of math, right? Do you think so?
I think statistics is not math because it depends on many factors.
Well, in math, you can deal with many variables as well. You have multiple calculus, right? In calculus 2, even though in calculus 2 you only consider the function of x and y, but in general you can deal with many numbers, right? You can deal with f of many variables. Okay, one student agree with the statement that in statistics you need to deal with a lot of formulas, and because there are too many formulas, too many numbers, calculations, you think that it is a part of math. Well, if you have a look at electrical engineering, you will see that there are a lot of formulas there as well. They need to use the fast Fourier transformation, a lot of things there. If you have a look at transportation, or let's say you have a look at research in transportation, or even in mechanics, you see that there are a lot of formulas and calculations there. Okay. All right. So like if you consider the if you consider the model in some models in electricity, for example, then you may need to deal with partial differential equations, and that is actually a lot of calculations there. Okay, so it is not the reason. Well, in fact, statistics is not a part of math. Why is that? The conclusion you can get in math is always true. That's the point. Okay. Okay. Now, if you get a plus b squared, what do you get? You get a squared plus 2ab plus b squared. This is always true. Okay. And from here, I can say that 1 plus 2 squared should be 1 plus 2 times 2 plus 2 squared, right? This is always true. Is that clear? That's all right? Okay? It is always true. 1,000 years ago, 1,000 years later, that is always true. However, in statistics, that is not always true. Okay, the statement you get, the conclusion you get in statistics is not always true. Suppose that you have the hypothesis that the velocity is greater than or equals to 50, and then h1 is that m is less than 50. Then, all right, you can come up with a conclusion that you fail to reject the null hypothesis by using a method. All right. Now, maybe tomorrow there is another method which is better. Okay, and that method can help you to conclude that you can reject the null hypothesis. Okay, so you see that the conclusion you can get in statistics is not always true. It may change over time. Okay, do you understand? So you can get this one, and then all right. So how can we get? So it means that there are a lot of methods that you can use in statistics, right, to test one hypothesis. And if there are many methods, you want to know which one is the better one, and you can have a look at the power of the test. You can use the power of test to compare the efficiency of the methods. All right, the method with greater power of test will be the better method. Okay, if that's all clear, here is the outline of what we are going to study. It is very similar to what we learned in the previous chapter. All the xi are independent, and they follow a normal distribution with the same mean, the same value sigma square. The first case is that you know sigma square. The second case is that you don't know that value. The third case is that they are independent, but you don't know the distribution. Then you need an extra assumption that n is big enough to be able to use the central limit theorem. And the last one will be the Bernoulli distributions it is that particular applications of the third case. Okay, and then you can test the hypothesis related to proportion. All right, so this is the outline of what we are going to study of the whole chapter. And I don't think that we have enough time to go over all the things, but I think the first case will be the more important case. I'm not saying that it is the important because it is what you will see in the final exam, but it is, I say it is important because it will give you the main idea of what you need to learn in the semester. All right. All right. So if you understand this example, you will understand the whole chapter, and if you understand this one, you understand the rest of the semester. Okay. All right. Let's start with the first example. The first case, and we start with an example. In fact, the first case is that all the xi, they are independent and they follow the same normal distribution with the same mean, the same variance. Okay, and you know the population variance. All right. Is there any questions so far? All right. Here is the question. 50 smokers were questioned about the number of hours they sleep each day. It was found that the sample mean is 7.5 hours, and suppose that the population has normal distribution with standard deviation 0.5 hours. Test at the 5% significance level the hypothesis that the smokers need less sleep than the general public, which needs an average of 7.7 hours of sleep. In this case, there are a few numbers you need to know. 50, okay, 50. You have 7.5 hours. Then you get 0.5 hours. Okay, 5% at 7.7. Okay. Now, what is that? The alternative hypothesis. You need to remember that you can only support the alternative hypothesis. All right. So what is the H1? Tell me, please. What is H1? Can you tell me, please? More than or equal to 7.7? Well, actually, that is X0. That is X0. H1 is what you want to confirm, and what you want to confirm is the mean value less than 7.7. Okay. Here, M is the number of hours that a smoker needs to sleep each day. Okay, then you get H1 and H0. M is greater than or equal to 7.7. Do you understand this one? Do you understand this? Is this all right? After you get this one, I will assume that F0 is true. All right. All right. Now, please have a look at the line. This is 7.7. Okay. And let's say this is 7.7, right? 7.7. And this is H bar. If H bar is too small, way too small, let's say only 2 hours. So it is much less than 7.7. And because we knew that H bar is just an approximation of M, then H bar and M are close to each other, right? So we see that M is close to H bar, so it should be around here. Okay, if H bar is much less than 7.7, we believe that M is less than 7.7. Okay, there's a chance that M is greater than 7.7, but that is really, really small. Okay, do you understand that? Is that all clear?
Yes, sir.
All right. Okay. So in this case, we can reject the null hypothesis, and then you can support S1. However, if H bar is close to 7.7, let's say 7.6, okay, then you see that H bar is close to M, or let's say M is close to H bar, right? So M could be here, or there, right? So M could be less than or greater than 7.7. You cannot guarantee anything. And then you fail to reject. You fail to reject H0. So you don't know if H0 is true or false. It could be true, it could be false, with big chance. so you cannot make any further conclusion. Do you understand? May I move on? Everybody? That's all clear? Okay. So here's the point. You can reject the null hypothesis if and only if X bar is too small, right? You reject it if X bar is too small, too less than, is much less than 7.7. And then you get X bar minus 7.7 is too small. Or you can standardize that to get X bar minus 7.7 over sigma over the square root of n is much less than 0. Do you understand that? Okay, and you know this one by C. On the other hand, we knew that X bar minus m over sigma over the square root of n that follows the standard normal distribution and 0, 1. Okay, is that all clear? We say that Z is too small if you can find a constant C so that Z is less than C. All right. So we say that so you see that you can reject the hypothesis if Z is less than some C. How can we determine the value of C? Well, you know, you can come up with the probability. You can come up with the probability that C is less than C. The probability that C is less than C is the probability that you are wrong. Okay, and that would be alpha. Okay, alpha is the probability that you allow yourself to be wrong, right? So you come up with the graph of the density curve for the standard normal distribution, and you get the value C here. This is alpha, right? This region is the rejection region, and this region is the acceptance region. Okay. So if the value C is less than C, we reject the hypothesis. If C is more than C, we fail to reject the null hypothesis. How can you determine the value of C? Because we are using the standard normal distribution, this value C is simply minus C alpha. Okay, the point is that the areas to the left is alpha. Is there any questions so far? Is that all clear? It's just like well, let me summarize what I just said.
Yes.
Well, you have this hypothesis m is less than 7.7 for H1, and you see that H0 is true, and you want to know how if you can say that H1 is true or not. You have a look at the line here. You have 7.7. If H bar is much less than 7.7, we think that m is also less than 7.7. If H bar is close to 7.7, still less than but close to 7.7, then we think that m may be greater than 7.7. There is a chance for that, and then we reject the hypothesis if H bar is much less than 7.7, or let's say you can find C such that Z is less than C. You compute the probability that Z is less than C, which is the probability that you allow yourself to be wrong, and that is the significance level alpha. If alpha is given, then you can determine the value of C, which is minus C alpha, right? So after all, what should we do? You need to find the value of C, right? You know X bar, you know sigma, you know n, they can find C. You can determine the value of C because alpha is given, and you can find the value of Z minus C alpha, which is C. You can compare C and Z and C and Z. If C is less than C, then Z belongs to the rejection region, and then you reject the null hypothesis. Otherwise, you fail to reject the null hypothesis. Is that all clear?
Yes, sir.
This is the one you have. All right. Okay. All right. Now I want to give you another to talk about another case. Suppose that I change the question a little bit. You get S0 is that the mean is less than or equals to 7.7, and H1 is that M is more than 7.7. Okay. Then you will reject the null hypothesis if H bar is much greater than 7.7, right? Or let's say the Z is greater than C. So you can have a look at the graph here. Z is greater than C. The probability that Z is greater than C is alpha. That's why this tail is alpha, right? And yeah, you're still using the standard number distribution, and this point is Z alpha. Is that clear, everybody? Is this all right? Next, if I change the question a little bit, let's say S0 is that the mean is equals 7.7, and H1 is that M is not 7.7. Remember that the equal sign is always with the null hypothesis. All right, you have this one, and then you can say that you will reject the null hypothesis if H bar is far from 7.7, or let's say H bar minus 7.7 is far from 0, and then you can come up with Z, which is H bar minus 7.7 over sigma over the square root of n. It is far from 0. All right. Or let's say Z, you can find you can, and then it is far from 0 if Z is less than minus C, or Z is more than C. That's all. Okay. You have a look at the graph here. You see that this is minus C, and C, this is 0. So Z is far from 0 if Z is over here or over there, right? And you get the rejection region. Make sense? And the probability of these two tails is alpha. So this tail is alpha over 2. So you get alpha over 2 and alpha over 2. And then you get the value Z alpha over 2 for this one, and minus Z alpha over 2. Do you understand? If that's all clear, everybody? If that's clear? May I move on? Okay, now in this case, so we just finished the first. We just finished the first case. What if you want to get a test when you don't know sigma square? So here in the second case, X1, Xn, they are independent. They follow the same number distribution, the same mean, the same variance. However, sigma square is unknown. All right. You can go all the way back here to see that you can use similar arguments, right? The only thing that you need to take care of is the distribution of the X bar, because you don't know sigma, right? If you don't know sigma, it is very natural to approximate sigma by S. Okay, you can approximate sigma by S. and then you get the H bar minus M over S over the square root of N. From what we learned in the previous chapter, it follows the distribution with degree of freedom n minus 1. And you can use this distribution to perform the test. Okay, so to perform the test, I'm going to compute the t value, which is H bar minus the values m0 over S over the square root of N, and then that will help you to make the conclusion. All right. Let's have a look at the following example. In a random sample of 20 components taken from a production line, the mean length of each component in this sample is 0.8.6 millimeters with a standard deviation of 6.3 millimeters. Given that each component should measure 105 millimeters and that the population distribution is normal, is there enough statistical evidence to show that the production line is producing components that are of an incorrect length, set at 5% level of significance? In this case, you may see that H1 is that you want to check whether there is enough evidence to show that the production line is producing components that are of an incorrect length. So H1 is that the mean length is not 105, right? M is the length, that is the M. And S0 is that M equals 105. Okay? Is that clear? So after you get S0 and H1, you can have a look at the the t value, which is H bar minus 105 over S over the square root of N. This is 108.6 minus 105 over S, which is 6.3 over the square root of N, and in this case is 20. Okay? And then you can get the value T. T is 2.556. All right? You can do the calculations to get that. And then you draw the graph here, right? This is a two-sided two-tail test, right? One M is not the same as 105, so you have two tails here. The significance level in our problem is 5%, so it should be 0.025 for each tail. All right, and we are using the t distribution with degree of freedom 19. Okay, and you can have a look at the t distribution table. The degree of freedom is 19. The area to the right is 0.025. So I will go back to the table up here, right? To get that, what do you have? You get the degree of freedom 19, and the area to the right is 0.025, right here. So you get 2.093. All right. So you can you go back here to get 2.093 for that, minus 2.093. You check to see that the t value belongs to this interval. It belongs to the rejection region. Therefore, we can reject the null hypothesis, right? Which means that we can conclude that the production line is producing components that are of an incorrect length. Is there any question so far, everybody? Is that clear? Is this all right? That should be okay, right?
Teacher, can I ask you again about the meaning of C in the formula?
Wait, which one?
The meaning of the C, like the C equals to Z alpha. So what is the meaning of the C?
What do you mean by C?
I mean in the formula.
I mean here?
Yeah.
Well, when you say that, look, when you say that Z is big enough or small enough, what does it mean? We say that Z is too small. It means that Z is less than something, right? So if Z is less than that number, we say that Z is small enough. If Z is greater than C, we say that Z is big. It's not small enough. All right. That is the threshold value.
So C is a number that if Z
It is the
smaller
threshold.
Yeah.
Okay. That makes sense?
It means that C is like a threshold to tell if it's too small or too big, right?
Mm-hmm. Yep.
Thank you, teacher.
Yep. So if Z is less than C, we say that C is too small. I mean, in this case, in this problem, right? So you get that C, you get that value C, and you compare Z with the C value here. All right. Any questions so far, everybody? It is okay. I think that's enough for today.